Okay, this is going to be the second part of chapter 16, and we're going to start out talking about strong versus weak acids. Alright, so strong acids are ones that separate into ions completely. And that's why in the first video, whatever we said, like if we had 0.020 molar of HCl, then we have 0.020 molar of the H+, because it completely separates into ions. Now, if it's a weak acid, or a weak base, it only partially separates into ions. Okay, and unlike a monoprotic strong acid, the H+ concentration is not the concentration of the acid. Now, a lot of times for an acid, we call it HA just for any generic weak acid, because A stands for acid, H stands for acids having an H in the front. So if I would react this with water, we're going to form H3O plus A minus, and this is like our generic example. Now we have a Ka for a weak acid, and Ka is your acid dissociation constant. And this is constant for one particular acid at a particular temperature. And there'll be a chart in your textbook that has a list of Kas for all of the acids that you would probably need. Okay, and if we look at our equilibrium constant, keep in mind this is a liquid, these are aqueous, so we would have H3O plus concentration times A minus concentration all over HA. The water doesn't show up in our expression because it is a pure liquid. So anytime we have a weak acid, we can't assume that the concentration is what the concentration of the acid is. We're going to have to find it. Alright, so let's say that we have a 0.10 molar solution of a weak acid. In this case, this is formic acid. And it is, pH is 2.38, and they are asking me to find Ka. So in this case, a lot of times you're given Ka and we are asked to find pH, and we'll do an example like that. So in this case I have HCOOH with water. We're going to form H3O plus and COOH minus. Now, if this part, like the equation should not be a confusing part. So if the equation bothers you and you want to just write HA every time, that's fine. Okay, so I don't know what my equilibrium concentrations are, and I need my equilibrium. So I'm going to set up what's called an ice chart. And this is initial, change, and my equilibrium. So initially I have 0.10 of this, and I don't have anything of this, and the water doesn't matter because that's pure liquid. I don't know how much ionizes usually in a problem, but in this case, since I know my pH, I can figure out the amount that ionizes. Okay, and my H plus is equal to 10 to the negative pH, so 10 to the negative 2.38. And this has 2 decimal places, so I'm going to round this to having 2 significant figures. So that's the amount of H plus that is formed, which means that's the amount that ionized. So 0.0042 plus 0.0042 plus 0.0042. So this is 0.0042, 0.0042, and this would be 0.1 minus that. Okay, so now I have my equilibrium concentrations. So Ka is my H3O plus times my COOH minus all over my HCOOH. And I'm just going to plug in the numbers that I got at equilibrium from this row. So 0.0042 times 0.0042 divided by 0.0958. So my Ka is 1.8 times 10 to the negative fourth. Now, a lot of times they're going to ask me to figure out the percent that was ionized. And to figure out the percent that is ionized, we're going to take the part that was ionized over the initial concentration times 100. So in our last example, go back here, the amount that was ionized was the 0.0042, and my initial concentration was 0.1. So I would be taking 0.0042 divided by 0.1 and times 100. So this one would be 4.2%. Okay, so now we're going to do an example where we're going to be given the Ka and asked to find the H plus. So let's say we have a solution that is 0.30 molar acetic acid. And Ka for acetic acid is 1.8 times 10 to the negative fifth. Alright, and this is a weak acid. So 0.30 molar. And this time I wasn't given my pH, so I don't know how much ionizes. So I'm going to say X ionizes. And my Ka would be H3O plus times C2H3O2 minus all over HC2H3O2. So this is going to be 1.8 times 10 to the negative fifth equals x squared over 0.30 minus x. Now, I don't want to do the quadratic, so we are going to make an assumption that this x, the amount that's ionized, is so small that 0.3 minus x is just 0.3. Okay, so we need to check this assumption and make sure this is small. So my percent ionized is 0.0023 over the initial, which was 0.3 times 100. And I get a percentage of 0.77%. And if percent is less than 3%, then the assumption is okay, which means you don't have to do the quadratic. Alright, so we found the H, or the X, and on my table up above, X is my H plus, and we were asked to find the pH. So pH is negative log of my H3O plus concentration. So negative log of 0.0023. Alright, and I had two significant figures, so I'm going to need 2 decimal places in my pH, and I got a pH of 2.63, which seems reasonable. Okay, so next we want to talk about polyprotic acids. Okay, and polyprotic acids have more than one H. So this could be like H3PO4 or H2SO4, something like that that has more than one H. And polyprotic acids have a first ionization, a second ionization, so you're going to have more than one Ka. For this one, we would have Ka1, we would have Ka2, and we would have Ka3. For this one, we would have just 2. So, for example, if you had H2SO4, it is first going to ionize one of the H's, and this is where we would use Ka1. Then the second one would ionize, and this would be Ka2. Now typically these Kas, especially Ka2 and Ka3, are very, very small. The bulk of your ionization comes from the first one. So a lot of times we can base our pH off of that first ionization, but not always. And I made a separate video just going through polyprotic acids. So that's pretty much all I'm going to say about those, because you can watch that other video. Alright, now we want to talk about weak bases. Now, weak bases are going to work just like weak acids, except we are going to use Kb, and we are forming OH minus. Alright, so we have an example. It wants to know what is the pH. So what is the pH of a 0.15 molar NH3? And Kb is 1.8 times 10 to the negative fifth. It's always kind of strange. The Kb for ammonia is the same number as the Ka for acetic acid. Okay, now remember, bases are acceptors. So we are going to form OH minus and NH4 plus. And I don't know how much of this, since it's weak, is actually going to split up into ions. So just like an acid, I use X, and I set it equal to my Kb. So 1.8 times 10 to the negative fifth would be equal to x squared over 0.15 minus x. We are going to assume that x is really, really small. So 1.8 to the negative fifth times 0.15, square root that. And I'm going to do my check over here. So the percent that's ionized, 0.0016 over 0.15. Make sure that assumption is valid. Alright, and I got 1.095%, way less than the 3% that's allowed. So that means my assumption okay. So this then is my OH minus concentration, because in this chart I form OH minus. So I'm going to do my POH, which would be negative log of my OH. Okay, so my POH, I got, let's see, 2 sig figs, so 2 decimal places, 2.78. But they asked me to find my pH, so my pH plus my POH is 14. So 14 minus 2.78 is going to be 11.22, still keeping with my 2 decimal places, and that would seem like a good pH for a base. Okay, so now we're going to talk about Ka and Kb. Alright, and Ka and Kb are related in that Ka times Kb is 1 times 10 to the minus 14th. So that means if I know the Ka, I could find the Kb for a particular, like if I knew the Ka for an acid, I could find the Kb for the conjugate base using this relationship between Ka and Kb. I can also use Ka and Kb to tell me something about a substance. So I know that the larger the Ka, then that means the stronger the acid is. Likewise, the larger the Kb, the stronger the base. So I could compare Ka and Kb to tell me if the substance is more basic or more acidic, or if it's neutral. If it's neutral, then Ka would be equal to Kb. If Ka is larger than Kb, then it's acidic. And if Kb is larger than Ka, then it's basic. And we'll be using this relationship when we're dealing with salts. And I made a separate video just covering salts. So let's talk a little bit about what salts are. And salts are ionic compounds, and they are made from an acid reacting with a base. Now, if we knew the Ka and the Kb, we could determine whether the salt is acidic, basic, or neutral. But we can also just look at the formula. So let's say that I have something like NaCl. So if we take the first part, Na, and we put it with OH, and then we take the second part of our salt and we put it with H. So NaOH is a strong base, HCl is a strong acid, so this salt is likely to be neutral. However, if I had something like NaF, this is made from a strong base and a weak acid, so this is going to be a basic salt. So whatever my salt is, I always take the first part with OH, the second part with H, then I can look at the strength of those acids and bases to determine whether it's going to be acidic, basic, or neutral. So if they're both strong, it's neutral. Whichever one is stronger, so if this was a strong acid and a weak base, it'd be acidic. In this case, the base is stronger, so it's basic. If you have a weak acid and a weak base, then you want to look at the Ka and the Kb to help you decide. Okay, then we're going to take a look at acid strength. And we're going to look at different types of acids. We're going to look at binary acids. We're going to look at oxyacids, and these are ones that have oxygen, so it's usually H with a poly ion. And then we are also going to look at compounds that we haven't looked at before, which are carboxylic acids. And they contain the grouping COOH. And this is called the carboxyl group. That's why they're called carboxylic acids. Alright, so we're going to just look at binary acids. Okay, and for binary acids, so like if we look at something like HF, the more polar the bond, the weaker the acid. And remember, you can decide how polar the bond is by looking at those electronegativity differences. The stronger the bond, the weaker the acid. Okay, for oxy, oh, I probably should, I maybe should mention that when we're talking about, no, never mind. Okay, we're going to go on oxy acids. For oxy acids, the more O's that you have, the stronger the acid. So if we had something like HClO, HClO3, this one has more O's, so it's going to be stronger than HClO. And for carboxylic acids, you're not going to be asked to look at different ones and decide the strength of those. So it's mostly going to be oxy acids and binary acids.